the alcohol, even though it is heavier. When a liquid wets a solid that has holes or crevices in it, it will be sucked in more and more strongly as the crevices get smaller and smaller. We can see this with two glass plates, touching on one side, but slightly separated on the other by a paper clip. The water rises between the plates, in this case into a hyperbolic curve, higher where the plates are closer. If a crevice is small enough, capillary action can raise liquids hundreds of feet high. On the other hand, if a liquid doesn't wet a solid, it tends not to enter holes. This is the principle of waterproofing cloth. All such capillary actions can be explained in terms of the two boundary conditions, the contact angles made by the liquid with the solid, and the pressure differences caused by the curved interfaces. Surface forces and the pressures they cause are the controlling factor in the breakup of jets and sheets of liquid. A cylinder of liquid, like this, will always break up into drops. The cylinder will be slightly uneven, and where it is smaller, the radius of curvature will be less, and the pressure higher. This higher pressure pushes liquid up and down into the larger, lower pressure, fatter region. What was small becomes smaller, and the cylinder pinches off into a set of drops. This occurs so rapidly that you cannot see it clearly by eye, but in slow motion, slowed down 200 times, one can see the initial disturbances amplifying. Lord Rayleigh calculated the speed at which these disturbances would grow, and he found that for a disturbance wavelength of about 4.5 times the diameter of the jet, the disturbance would grow most rapidly. This is about what one sees happening. Surface tension also causes the rupture of sheets of liquid. This soap film, being shown in slow motion, slowed down 300 times, will be touched by a pencil that has been dipped in alcohol. A liquid film can become thinner by stretching or by evaporation. If its thickness reduces to a distance of the order of magnitude of the distance between molecules, then a hole may appear. Once a hole appears, then surface tension will pull the edge along, in effect gobbling up the film. The pulling force of the film, twice the surface tension, is balanced by the momentum flux of the liquid entering the rolled up edge. The velocity is high. The edge of a film about 1/1000th of an inch thick would zip across a room in less than a second. Another jet breaking up into drops is shown here, where a water jet falls on the end of this metal cylinder. In slow motion, the breakup shows more clearly. The rolling up edge advances into the sheet of liquid, advancing faster where the sheet is thinner. Drops are produced by breakup like this in many things, from fuel nozzles to lawn sprinklers. When the cylinder is moved, the sheet will take on many different forms. It can even bend back sharply upon itself, apparently violating conservation of momentum. If you think about it, however, the sheet couldn't go out beyond the radius where the surface tension is equaled by the radial momentum flux of the liquid. It is at that radius that the water changes direction sharply. For some time, we've talked about phenomena that involve the pressure difference caused by curved interfaces. Here's a beautiful example showing many of these phenomena. A drop of milk that in slow motion will hit a thin layer of water. The drop spreads sideways, and its impingement on the static water sends up a liquid sheet. The rolling up edge of this sheet is unstable and forms a coronet, which is pulled down by surface tension. Part of this liquid moves inwards where it meets to form a spike. The spike in turn is pulled down by surface tension. Surface forces lead to a third boundary condition that should be used with the equations of fluid mechanics. If the surface tension varies along a surface, then the surface must move. Consider a boundary between a liquid A and another fluid, such as a gas B. Think of a unit length of the boundary and the forces acting on it. It will be pulled in this direction by surface tension, and it may be pulled in the other direction by a slightly larger surface tension. If it is, then the surface will move, and it will move in that direction, carrying the boundary fluid with it. It will move at such a velocity that the shear force it exerts on the liquid and the shear force it exerts on the gas will just equal the added surface tension. That is, the variation of surface tension along a surface is balanced by shear forces in the bounding material. The gradient of the surface tension will be equaled by these shear forces. There are three things that cause variation of surface tension: the kinds of molecules that get into surfaces, the electrical conditions at the surfaces, and the temperature of the surfaces. For example, ether molecules lower the surface tension of water. If I take a solid block and spread a thin layer of water upon it, and let ether molecules fall on the water, the surface continually moves away. Through viscosity, it drags the underlying water along with it until eventually it leaves a bare spot. A drop of alcohol also lowers the surface tension and very quickly causes a bare spot. This surface tension pumping action shows up well with a dyed mixture of alcohol and water. Swirling the mixture around the glass leaves a thin film on the side. Evaporation of alcohol from that film causes it to have a lower proportion of alcohol and therefore a higher surface tension